I think you have to be pretty good and have to work a lot, there's no question, but it's also a matter of luck. There's no point, you have to be lucky to be at the right moment, at the right point to ask the right questions. And that is a very complicated setting which you cannot steer at the beginning.
During your career, you have also been in academia, but also in industry. So can you say what you've took out of this, what is important for your job today?
Yeah, I was in for some time, or for a shorter time, in two companies. One was Exxon Research and Engineering, but this was a research lab. So after the oil crisis, Exxon decided that oil is much too valuable just to burn it. And because of that, they decided to set up what they called Bell Labs of Chemical Physics. And that was a lab in Annandale, New Jersey. And where they collected the who is who of senior and junior people, mostly in the US, to build up a new basic research lab. And I happened to be there as a postdoc. That was the first stage. The second one was shortly before I came here. I was for several years, I was staff scientist at the research center in Jülich. And I wanted to do something different. And in the context of a BMBF project, I met several people from Bayer at the time, and we started a discussion, and we decided that it might be good for me to come for some time and see whether this would be something for me. And there I learned a lot about how research in industry works, or worked at that time. I think nowadays it's different. And in the end, it was a question whether I would stay in industry or whether I would go to the Max Planck Society. And eventually I decided to go to the Max Planck Society.
So what do you like better here?
The Max Planck Society offers unique opportunities to really do long-standing research. If you follow a long-standing idea, especially when you have ideas, or think you have ideas, let's put it that way, which are in a stage where it's very difficult to get funding from the FG or nowadays EU, but that time was just the FG or so. In the Max Planck Society, you can follow these ideas and develop fields.
And which polymers do you find especially exciting at the moment?
At the moment, we are working in two different directions. One is in the direction of phase behavior of systems where mixed solvents play the role, so-called smart polymers like polynipam or so. That's one direction. The other direction is not directly connected to a specific polymer, namely it's the question of the role of topological constraints, namely the fact that two polymer chains cannot cross through each other. And this is not only a complication of changing the viscosity, you can also use that to make new materials, to structure materials in a systematic manner. Mm-hmm. And that is the second line of questions I'm personally involved in, but the theory department here is of course much wider. We are more interested in structural behavior and trying to connect chemical aspects and generic physical aspects.
And why are you so interested in bringing the chemistry and the physics world together, or how did that happen?
Because that's what makes the versatility of polymers. You have, on the one hand, you have a physics-dominated or generic properties in the language of statistical physics. On the other hand, you have a chemical specificity, and the combination of the two makes this enormous versatility of macromolecular materials. And that is where I think also the physics world and the chemistry world come together, and that it's, from my point of view, really interesting.
How have the methods of computer simulation evolved since you've started with them?
First of all, I would like to say the field from, let's say, the late 80s on expanded dramatically. And it expanded dramatically for many reasons. One was the better computers, the advent of vector computers like Cray and so on, and then parallel computers. But also equally important was software development and also theory development with respect to multi-scale modeling. And this led to an enormous development of the field, but also a little bit a loss of focus, no? Because of the many different opportunities you have from chemistry. It's very difficult to identify the one question or so. No? The development, I think, will go in different directions. On the one hand, there are still many basic questions originating from the physics side, like the question of the nature of a glass transition, where polymers might be a very interesting, again, example system to study specific questions. But this is a smaller development. Another thing is in the context of machine learning. I'm not an expert in machine learning, I have to say, but it's already established that machine learning is extremely good to produce excellent force fields. And force fields, when you do a simulation of a system, typically you integrate Newton's equation of motion, so you do classical mechanics. But when you look into the local details of a chemical system, in principle you would have to do quantum mechanics. No? And at that point, there is a development coming from the DFT community, which shows that force field development with the help of machine learning techniques is extremely powerful. And this will become, I'm pretty sure that will become standard in the field and will be very important. But then there is another development where I think especially biology is playing back interesting questions into physics and chemistry. So when we started in the context of the N-to-zero theorem, it turned out that polymers were very interesting materials to do new physics. But now what is coming back from biophysics are questions where I think theory especially, but that includes chemistry and physics, still is quite underdeveloped. And one field, for instance, is phase behavior, transient phase behavior of multi-component systems. So when you look at typical alloys in metallurgy or mixtures in polymer systems, you have 2-3 different polymers and maybe a few additives as viscosity modifiers or so. When you look at a biological system in a cell, you have hundreds or thousands of components and one would like to understand how can one steer, control or understand phase behavior when you have hundreds of systems. They even do not properly know the interaction constants. And there we are at the very, very beginning.
So what keeps you inspired and motivated in your job?
There are so many interesting things which we do not understand. That's very simple.
What is success in your opinion?
Understanding something.
And how would you become a successful scientist?
I think you have to be pretty good and have to work a lot, there's no question, but it's also a matter of luck. There's no point, you have to be lucky to be at the right moment, at the right point to ask the right questions. And that is a very complicated setting which you cannot steer at the beginning. From then on you can do a lot. And
interdisciplinarity is very important for you. Why is that?
You need the knowledge from different disciplines to really have long-standing progress. But at the same time, the people who work in these projects have to be well rooted in their discipline. Otherwise, you do not reach the level of excellence you need.
And when the general public hears polymers, they often think of, I don't know, bottles or plastic bags or something. And then, of course, the environmental impact they have. But there are also these huge advantages and the needs we have for polymers. So do you address that somehow?
We are not working on biodegradable polymers from the theory side, but we make this clear to everybody that there are these two sides. There is, for instance, a special program here at the university of interdisciplinary courses where we gave several lectures on pros and cons of the application of polymers, and where Thomas Wilges was involved, I was involved, but also Katharina Landwester were involved. And we have here also the educational path around the institute about the use, the chemistry, physics and use and application of polymers, and where we address all these topics from applications but also the environmental concerns of polymeric systems.
And so this polymer path everybody can take or go there
It's mostly used by schools, but you can also kind of book it. It's not open in a way that simply people can run around the institute, but it's for public. Okay. It's for the public.
What other interests do you have outside of science?
I have a big family, so we have grandchildren now who are at the age that they're happy to see me, and I'm happy to see them. So I'm quite busy.
Great. So thank you very much.
You're welcome.